Hello and welcome to Science Night Tales. I am glad you have found this quiet moment to drift. Tonight, we are going to travel far beyond our own solar system. We often think of planets as being like the ones we know, rocky like Earth or gaseous like Jupiter. But the universe is full of worlds that defy our imagination. We are going to visit planets where it rains glass, worlds that drift alone in the dark, and planets locked in an eternal stare with their stars. We will see that, despite their strange and extreme conditions, they are all governed by the same simple, elegant laws of physics that hold our own world together. You do not need to memorize data tonight. You are safe to observe from a distance. You can simply let the variety of the cosmos wash over you. If this perspective helps you find calm in the vastness, you are welcome to like or subscribe. For now, let go of the familiar and let's explore the unknown together. Beyond our own solar system, astronomers have now confirmed more than 6,000 exoplanets, 6,000 distinct worlds, each one orbiting a distant star, each one following its own quiet path through the darkness of space. This number continues to grow with every new observation, every careful analysis of light curves and radial velocity shifts. 6,000 is already a remarkable count, yet it represents only a tiny fraction of what likely exists in the Milky Way alone. Among these thousands of confirmed exoplanets, some stand out immediately because of how strange they appear when compared to the planets we know here in our own system. Consider, for example, the class we call hot Jupiters. These are gas giants, similar in size to Jupiter or even larger, but they orbit so close to their host stars that their surface temperatures soar to thousands of degrees. Their atmospheres are swollen and extended, sometimes escaping into space under the relentless bombardment of stellar radiation. The intense heat keeps them from having anything like the calm banded clouds we see on Jupiter. Instead, their envelopes are sculpted and stripped by the star's energy. Then there are the rogue planets, worlds that drift freely through interstellar space with no star to call their own. These planets receive no steady light, no warmth from a parent star. They float in permanent darkness, yet some may still hold onto internal heat left over from their formation, enough to maintain subsurface oceans or thin atmospheres beneath layers of ice. They are solitary travelers, carried along by the gentle pull of the galaxy's overall gravity. Another type that captures attention right away is the tidally locked world in a star's habitable zone. These planets keep one face permanently turned toward their star, so one hemisphere experiences endless daylight while the opposite side remains in eternal night. The day side can be extremely hot, the night side extremely cold. Yet a narrow twilight ring between the two extremes might allow for conditions where liquid water could exist if the atmosphere circulates heat effectively from one side to the other. These are just a few examples among the many thousands already confirmed. Scorching hot Jupiters, completely dark rogue planets, tidally locked worlds with permanent day and night sides. Each one is so different from the others, and so different from anything in our solar system. And yet, all of them, every single one, exists and behaves according to exactly the same laws of physics we already understand here on Earth. The same gravity that keeps our moon in orbit, the same thermodynamics that governs heat flow in our atmosphere, the same chemistry that forms molecules in our clouds and oceans. The same simple rules produce all this astonishing variety. It is a quiet thought, isn't it? How many completely different kinds of worlds can exist when everything is still governed by the same unchanging laws? Let us take a slow journey together now. Let us move gently from one type of world to the next, exploring the diversity step by step, and see what these distant places can show us about the order that underlies everything. We will go carefully, without hurry, allowing each category to unfold in its own time. Now, let's begin, very slowly, with the worlds that orbit closest to their stars. These are the planets that live in the most intense heat, right at the edge of what a world can endure. We call many of them hot Jupiters. They are gas giants, very much like Jupiter in our own solar system, sometimes even larger, with masses several times greater than Jupiter's. Yet they circle their stars at distances far smaller than Mercury's orbit around our Sun. Some complete an entire year in less than 3 Earth days, some in under 1 day. The distance is so small that the star's gravity pulls very strongly, and the planet's surface temperature rises to between 1,000 and 3,000 degrees Celsius, or even higher in the most extreme cases. At these temperatures, metals can vaporize, and the atmosphere becomes enormously swollen. The gas envelope stretches outward, sometimes to several times the planet's original radius, creating a very low-density, almost comet-like tail in some cases. The intense stellar radiation pours down constantly, without any night to offer relief. Day after day, year after year. The same side faces the star, because most of these planets are tidally locked, or nearly so. The heat drives powerful winds that race around the planet, carrying hot gas from the day side toward the cooler Terminator regions. Yet even those winds are orderly, governed by the same basic principles of fluid dynamics and energy transfer that we study in Earth's atmosphere. On the hottest of these worlds, the upper atmosphere glows faintly in infrared because the temperature is so high. Some models suggest that molecules of titanium oxide or vanadium oxide can form clouds that absorb light and make the planet appear even darker or stranger in color when viewed from afar. In certain cases, the dayside temperature becomes so extreme that rock itself can vaporize, creating a thin silicate atmosphere that rains out as liquid droplets on the slightly cooler night side or Terminator Zone. These are not chaotic processes. They follow precise rules of vapor pressure, condensation points, and radiative cooling. The star's radiation strips material away layer by layer over millions of years, sculpting the planet, reducing its mass, sometimes leaving behind only a rocky core wrapped in a thin remnant envelope. Astronomers call this process photoevaporation. It is slow, patient, and completely predictable once we know the star's luminosity and the planet's distance. Even as material escapes, the planet remains held firmly in its orbit by the same gravitational force that keeps everything in place. Now consider the ultra-short period planets, a related group even closer to their stars. These are often smaller, sometimes Earth-sized or super-Earth-sized, with orbital periods as short as 4 hours or 5 hours. Their surfaces, if they have solid surfaces at all, are bathed in such relentless heat that any atmosphere would be thin and constantly replenished by vaporized rock. Some show evidence of thermal emission so strong that the planet glows, faintly visible in infrared surveys. The day side can reach temperatures where iron can exist as vapor, and the night side, although still extremely hot, is cooler by hundreds of degrees, creating sharp temperature gradients that drive supersonic winds. Yet again, these winds, these temperature differences, these escaping gases, all behave according to the same equations of heat transfer, momentum conservation, and radiative balance that apply everywhere. Nothing random, nothing arbitrary. Just the quiet application of fundamental physics pushed to its limits. These close-in worlds teach us something important right from the beginning. They show us what happens when a planet is too close, when the star's energy dominates, when gravity and radiation work together to create conditions that seem almost impossible from our perspective. Yet every detail, every swollen atmosphere, every escaping molecule, every glowing cloud follows the rules we already know. There is a calm order, even here, in the most extreme heat. These worlds show us what happens when a planet is too close. But what happens when a planet is completely cut off from any star? Now let us turn, very gently, to a different kind of world. These are the planets that have no star at all. We call them rogue planets or free-floating planets. They do not orbit any sun. They travel alone through the vast darkness between the stars. Imagine a world born in the usual way, within a disk of gas and dust around a young star, forming just like any other planet, gathering rock and ice and gas, building a core, developing an atmosphere perhaps. But then something happens. A close gravitational encounter, perhaps with another planet in the same system or with a passing star, gives it a sudden strong tug. The planet is ejected, flung outward, away from its birth star and away from any orbit. Once free, it simply continues moving, carried by the momentum it had at the moment of escape, following a straight path through interstellar space, unless some other distant gravitational influence gradually bends its course. Most rogue planets we have detected so far are likely gas giants, similar in mass to Jupiter or Saturn, perhaps a few times more massive, but some may be smaller, icy worlds, or even rocky super-Earths. Because they receive no light from a star, their surfaces are extremely cold. Temperatures can drop to tens of degrees above absolute zero, colder than the surface of Pluto, colder than anything in our outer solar system. Yet, even in this deep freeze, some of these worlds may not be completely dead. During their formation, they trapped a large amount of heat from gravitational compression, from radioactive decay of elements in their interiors, from the energy released when planetesimals collided and merged. That internal heat, though faint compared to a star's output, can persist for billions of years. On a rogue planet with enough mass, this leftover warmth can keep the interior active, perhaps even molten in places, long after the surface has frozen over. Beneath the thick layer of ice, there could still be a liquid water ocean, kept from freezing solid by that slow internal heat, and perhaps by tidal heating if the planet has moons, or by pressure from the overlying ice. Such an ocean, isolated from sunlight, would be dark, but not lifeless in principle. Chemical energy. From serpentinization reactions between water and rock, or from radiolysis, could provide sources of energy, much like the deep-sea vents on Earth that support ecosystems far from the Sun. Some models suggest that thick hydrogen or helium atmospheres captured during formation might remain, acting as a blanket, trapping the internal heat, making the surface slightly warmer than it would be otherwise, perhaps allowing a thin layer of liquid volatiles or exotic ices to persist. Other rogue planets, especially the smaller ones, may lose almost all their atmosphere over time, leaving behind a bare icy surface or a rocky core exposed to cosmic rays and the cold vacuum. Yet even these barren ones still exist, still follow their paths, still obey gravity, still carry the story of their formation written in their composition. How do we find them? Most rogue planets are discovered through gravitational microlensing. When one of these dark worlds passes in front of a distant background star, its gravity briefly bends and magnifies the star's light, creating a characteristic brightening that rises and falls over days or weeks. The event has no repeating cycle because the planet is not orbiting anything visible, so these are one-time signatures, but they are unmistakable when seen. A few have been found through direct imaging in very young star-forming regions, where the planet still glows faintly from formation heat, appearing as a tiny infrared point moving across the sky. The infrared surveys, like those from the James Webb Space Telescope, are beginning to reveal more, especially the coldest, oldest ones that emit only the weakest thermal radiation. Estimates vary, but many astronomers now believe rogue planets may be as common as, or even more common than, stars in the galaxy. Some studies suggest there could be billions, perhaps tens of billions, wandering silently through the Milky Way. Each one, a complete world, formed under the same rules, ejected by the same gravitational dance, now drifting alone. They remind us that a planet does not need to orbit a star to be a planet. It only needs to be a body massive enough to become spherical under its own gravity, and to have cleared its orbital path, or at least to exist independently. The definition holds, even in darkness, even in solitude. These planets survive without a star, yet many worlds orbit their stars very far away, in cold and distant regions. Far from their stars, these worlds are dominated by cold. We now turn to the planets that orbit at truly vast distances, where the light of their parent star arrives as only the faintest whisper. These are the cold and distant giants, gas giants and ice giants placed on extremely wide orbits. Some circle their stars at hundreds of astronomical units, distances so great that a single orbit can take thousands or even tens of thousands of Earth years. The sunlight they receive is weak, often less than 1%, sometimes less than 1,000th of what Jupiter gets from our Sun. As a result, their upper atmospheres are extremely cold. temperatures can drop to around 50 Kelvin or even lower in the outermost layers. Yet these planets remain massive, many times the mass of Jupiter, with thick envelopes of hydrogen and helium that dominate their structure. Because they are so far out, the stellar radiation is too feeble to drive strong atmospheric escape, so their thick gaseous layers stay in place, preserved over billions of years. Inside these envelopes, the pressure increases steadily with depth, creating layers of exotic states of matter. In the colder ice giants, especially those rich in water, ammonia, and methane. Models suggest that carbon can crystallize under high pressure, forming diamond rain. Carbon atoms, squeezed and cooled, arrange themselves into diamond structures that slowly sink through the fluid interior, releasing gravitational energy as they fall, which in turn helps maintain some internal warmth. This is not a violent storm, but a slow, orderly process, governed by phase diagrams and thermodynamic equilibrium. Even in the gas giants on wide orbits, the deep interiors remain hot from formation energy and slow gravitational contraction, though much cooler than their close-in cousins. The seasons on these distant worlds, if they have significant axial tilt, are extraordinarily long. One hemisphere might face the distant star for centuries, receiving a thin trickle of light, while the opposite hemisphere remains in near total darkness for the same span of time. The atmosphere responds slowly. Winds are gentle. Cloud patterns shift over decades. Methane and other volatiles condense and sublimate on timescales that span human lifetimes. From our vantage point, these planets reflect only a tiny amount of the star's light, appearing as faint, reddish points in the sky, sometimes barely distinguishable from background stars. Yet infrared telescopes can detect their own thermal glow, the faint heat leaking from the interior, allowing us to measure their temperature, their size, and even some atmospheric composition. In certain cases, these wide-orbit giants may have captured moons during their long history, or retained rings. Though the rings are often thin and dark, composed of icy particles that reflect almost no light. Some may even host atmospheres rich in heavier molecules, such as carbon monoxide or phosphine, that form hazes or clouds at very low temperatures. All of these features, the diamond rain, the glacial seasons, the faint reflected glow, the preserved thick envelopes, arise from the same basic physics. Gravity holds the mass together. Thermodynamics dictates the temperature gradients. Chemistry determines which molecules condense or remain gaseous. Nothing here is accidental. Nothing is beyond explanation. The extreme distance simply pushes the same familiar laws into a different regime, revealing how robust those laws truly are. We see giants, massive and quiet, floating in the outer reaches, receiving only the weakest touch of starlight, yet still existing, still structured, still following the rules. Far from their stars, these worlds are dominated by cold, but closer in, we find planets with sizes and compositions very different from anything in our solar system. It's closer in. We find planets with sizes and compositions very different from anything in our solar system. These are the worlds that fall between the familiar giants we know and the small rocky planets like Earth. We call them super-Earths and mini-Neptunes. Super-Earths have masses between about 1 and 10 times that of Earth, sometimes up to 15 times, making them denser and more massive than our home planet, but still potentially rocky at their core. Their radii are typically 1 to 2 times Earth's, depending on how much atmosphere they hold, and their surface gravities can be 1.5 to 3 times stronger than ours. Because they are more massive, they can retain thicker atmospheres over longer periods. Atmospheres that might contain hundreds of times the mass of Earth's air. Some super-Earths appear to have deep oceans of water covering their entire surface, with pressures at the bottom so high that water exists in exotic high-pressure ice phases or supercritical states. The rocky surface beneath, if it exists, would experience immense weight from the overlying ocean and atmosphere, possibly leading to different styles of geology. Plate tectonics might still occur, driven by internal heat from radioactive decay and residual formation energy. But the plates could be thicker, the movement slower, the mountain ranges lower under such gravity. Other super-Earths might lack significant water, instead featuring thick atmospheres dominated by carbon dioxide or nitrogen, creating intense greenhouse effects with surface temperatures ranging from temperate to hundreds of degrees. Denser atmospheres mean stronger weather patterns, deeper cloud layers, and more efficient heat distribution. So even if one side faces the star more directly, the global temperature stays relatively even. These worlds challenge our simple categories. A super-Earth might have a rocky core, a mantle of silicates, and an atmosphere so massive it blurs the line between planet and gas dwarf. Their densities, measured through transit timing variations or radial velocity, range from 5 to 10 grams per cubic centimeter, higher than Earth's 5.5, suggesting large iron cores or high-pressure mineral phases in the mantle. Now, alongside the super-Earths, we find the mini-Neptunes. These planets have radii between 2 and 4 times Earth's, but masses only 2 to 20 times Earth's, giving them low densities, around 2 to 3 grams per cubic centimeter. They are not rocky, but enveloped in thick hydrogen and helium atmospheres that make up much of their mass, much like Neptune, but smaller overall. Beneath the deep gaseous envelope, there might be a layer of high-pressure water, ammonia or hydrocarbons, kept fluid by the planet's internal heat and immense pressure from the overlying atmosphere. Some models show these water layers compressed to thousands of times Earth's ocean pressure, forming exotic ices or supercritical fluids that flow slowly under the hydrogen ocean above. The transition from the hydrogen-helium atmosphere to the water layer below happens gradually, with no clear surface, just increasing density with depth. Atmospheric retention is key here. The thick hydrogen envelope traps heat, prevents hydrogen escape, and creates hazy upper layers, rich in photochemical products that make the planet appear dim even when transiting its star. Mini-Neptunes often orbit closer than Neptune does in our system, receiving more stellar heat, which expands their atmospheres and drives stronger internal convection. Winds in these envelopes can reach hundreds of meters per second, carrying heat from the inner to outer regions, much like on Neptune, but on a smaller scale. Yet the physics remains the same. Coriolis forces from rotation, pressure gradients, radiative cooling at the top, all balanced to create stable circulation patterns. Some mini-Neptunes show evidence of a core, perhaps 10 to 20 Earth masses of rock and ice, surrounded by thousands of kilometers of hydrogen, with a water-rich envelope in between. Their low density means they would float in water if such a test were possible. A clear sign that gas dominates over rock. These worlds fill a gap in our understanding, showing how planetary formation can produce such variety, depending on where and when the solids and gases condense in the protoplanetary disk. A super-Earth forms closer in, where rocky materials abound, accreting atmosphere but not runaway gas, while a mini-Neptune forms a bit farther out, capturing more hydrogen before the disk dissipates. Both can migrate inward later through disk interactions, ending up in orbits where we detect them, with compositions reflecting their birthplaces. Plate tectonics on super-Earths, if present, would recycle crusts slowly under higher gravity, building continents differently, or perhaps keeping one global ocean, with volcanic islands rising and sinking over eons. Atmospheric retention allows long-term stability, protecting the interior, moderating temperatures, and enabling complex chemistry that might persist for billions of years. Mini-Neptunes, with their deep envelopes, experience no surface weather as we know it, but global convection cells that mix material from deep inside to the hazy stratosphere. Infrared observations reveal their spectra, showing water vapor, methane, carbon dioxide in proportions that hint at the envelope below. These intermediate worlds expand our view of what a planet can be. Neither quite like the giants we explored before, nor the small worlds to come. They show endless combinations of core mass, envelope thickness, and migration history. Densities from airy 2 grams per cubic centimeter to dense 10 grams. Surface pressures from Earth-like to thousands of bars. All possible, all observed, all explained by the same formation models. The possibility of diverse surfaces, thick oceans on super-Earths, fluid water layers under hydrogen on mini-Neptunes, opens quiet questions about chemistry and stability over cosmic timescales. Yet every feature, every density measurement, every hazy spectrum aligns with the physics we know, from lab experiments to simulations to observations. These worlds show us many possibilities for rocky or gaseous surfaces. But some planets face an even more unusual situation, being permanently locked to their star. These worlds have two very different hemispheres. We now come to one of the most intriguing configurations we have discovered among distant planets. These are the tidally locked worlds in the habitable zone. Tidal locking occurs when a planet's rotation period exactly matches its orbital period around its star. As a result, one side always faces the star, receiving constant daylight, while the opposite side remains in perpetual darkness. This is the same phenomenon that keeps one face of our moon always turned toward Earth, but on a planetary scale, and much closer to the star. Many of these planets orbit red dwarf stars, which are smaller and cooler than our Sun, allowing the habitable zone, the region where liquid water could exist on the surface, to be much nearer to the star. The orbital distances are often only a few million kilometers, sometimes less than the distance from Mercury to our Sun. Because of the close orbit, tidal forces from the star are strong, slowing the planet's rotation over time until it locks, with one face permanently illuminated and the other forever in shadow. The day side, bathed in steady starlight, can reach very high temperatures, sometimes hundreds of degrees Celsius, depending on the star's brightness and the planet's atmosphere. The night side, receiving no direct light, cools dramatically, often dropping far below freezing, sometimes to temperatures colder than the outer solar system. Yet, between these extremes lies the twilight zone, or Terminator region, a narrow band encircling the planet where the star sits perpetually on the horizon. In this ring, the light is low but constant, creating a perpetual dawn or dusk, where temperatures may remain mild enough for liquid water to pool, if other conditions are right. The contrast is stark: extreme heat on one hemisphere, extreme cold on the other. Yet the planet as a whole must somehow balance the energy it receives. This balance happens through atmospheric circulation. On planets with a substantial atmosphere, winds carry heat from the day side toward the night side. These winds can be strong, sometimes reaching hundreds of kilometers per hour, driven by the larger temperature difference. The air rises over the hot day side, flows high in the atmosphere toward the night side, cools, sinks, and returns along the surface, forming a global Hadley-like circulation, but stretched around the entire planet. On the day side, clouds may form from evaporated water or other volatiles, reflecting some of the incoming starlight, helping to moderate the temperature. On the night side, those clouds can rain out or freeze, depositing ice or snow, which builds up over time unless the circulation brings enough heat to melt or sublimate it again. Some models show that the Terminator Zone could develop thick cloud cover, acting as a natural thermostat, trapping heat at night and shading the day side, potentially keeping surface temperatures within a range where liquid water could persist in lakes, rivers, or shallow seas along the twilight ring. If the atmosphere is thin, the contrast becomes sharper, with the day side scorching and the night side freezing solid with almost no heat transfer, creating a planet divided into two distinct climates. If the atmosphere is thicker, heat redistribution becomes more efficient and the global temperature gradient flattens, making the entire planet more uniformly temperate, even though one side never sees darkness and the other never sees light. In some cases, the atmosphere can develop standing waves or jet streams that circle the planet, carrying moisture and heat in predictable patterns. These circulation patterns are not chaotic. They follow the same principles of atmospheric dynamics we use to model Earth's weather, adjusted for the fixed heating pattern. The Coriolis effect, due to the planet's rotation, still shapes the winds, though the rotation is slow, often once per orbit, so the effect is weaker than on Earth. Yet it is enough to organize the flow, creating symmetric patterns, quiet and steady. Some tidally locked planets may have atmospheres rich in carbon dioxide or methane, enhancing the greenhouse effect, trapping more heat on the night side, and allowing liquid water even farther from the Terminator. The others, with thinner air, might have surface ice caps on the night side, extending toward the twilight zone, where melting could create temporary seas. Observations through transmission spectroscopy, when the planet passes in front of its star, reveal the composition of these atmospheres, showing water vapor, carbon dioxide, or clouds in some cases. The starlight filters through the limb of the atmosphere, telling us about temperature, pressure, and chemistry, even though we cannot see the surface directly. These worlds fascinate us because of the symmetry, the perfect division between eternal day and eternal night, yet the possibility of a narrow habitable band where conditions might resemble Earth's more closely than we first expect. The contrast is profound, yet orderly. The day side receives steady energy. The night side radiates it away. The atmosphere moves to equalize, all following the same laws of energy conservation, radiative transfer, and fluid motion. Nothing here defies physics. Everything aligns with what we already understand. The geometry is unusual, but the underlying rules remain unchanged. These worlds have two very different hemispheres, yet the atmospheres themselves can be some of the strangest features we have detected so far. These worlds show us many possibilities for rocky or gaseous surfaces. But now we come to the strangest atmospheres and surfaces we have actually detected. Among the thousands of exoplanets we have studied, a small number stand out because their atmospheres and surfaces behave in ways that feel almost otherworldly. Yet every detail has been carefully measured and explained. Let us move through them slowly. First, consider the planets so hot that their clouds are made of vaporized metals. On some of the closest-in hot Jupiters, the dayside temperature climbs high enough that iron, magnesium, and other metals exist as gas in the upper atmosphere. These metals condense into tiny droplets when they are carried by winds to slightly cooler regions, forming clouds of iron oxide or silicate vapor that scatter and absorb light in unusual ways. The result is an atmosphere that can appear very dark, almost black, because the metal clouds block much of the incoming starlight. In some cases, the clouds are so reflective at certain wavelengths that the planet shines with a strange metallic sheen when viewed in infrared. Next, there are worlds where the rain is made of glass. On a few extremely hot planets, silicon and oxygen atoms in the atmosphere combine into silicate molecules, which remain gaseous in the hottest layers. As these molecules are lofted upward and then cooled slightly, they condense into tiny droplets of molten glass. These droplets fall as rain, but because the temperatures are still thousands of degrees, the glass rain evaporates again before it can reach the deeper layers, creating a constant cycle of condensation and evaporation. The process is slow, orderly, and completely controlled by temperature and pressure gradients. Some models even suggest that on the hottest daysides, this glass rain can form a permanent haze, giving the planet a smooth, featureless appearance in visible light. Then there are the planets where the surface itself may be an ocean of lava. A few rocky worlds, especially those on very short-period orbits, receive so much stellar energy that their entire day-side crust is thought to be molten. Rock melts into a global magma ocean, tens or even hundreds of kilometers deep, with temperatures high enough to vaporize silicates and metals. The night side, though still very hot, cools enough for the magma to solidify, creating a sharp boundary between liquid and solid rock. Winds above this lava ocean carry vaporized material from the day side to the night side, where it condenses and falls back as molten droplets, feeding the cycle. The surface glows, radiating intense infrared light, so strong that some of these worlds have been directly detected in thermal emission. Sulfur-rich atmospheres are another extreme we have observed. On certain planets orbiting very close to active young stars, sulfur compounds dominate the upper layers. Hydrogen sulfide, sulfur dioxide, and elemental sulfur form thick hazes and clouds, giving the planet a yellowish or brownish tint in transmission spectra. These atmospheres are chemically reactive, with sulfur cycling between gas and condensed forms, depending on temperature and ultraviolet light. The deep pressure layers on many of these worlds reveal even stranger conditions. As we descend deeper into the atmosphere, the pressure rises rapidly, reaching hundreds, thousands, or even tens of thousands of times Earth's surface pressure. At these levels, hydrogen can become metallic, conducting electricity, generating powerful magnetic fields in some cases. Water, if present, is compressed into exotic high-pressure ices, sometimes called Ice 7 or Ice 10, which behave more like solids than liquids, yet still flow very slowly over geological time. Carbon, under the same extreme pressure, can form diamond structures, and in some models, diamond rain becomes possible, with solid diamonds slowly settling through the fluid interior. On the coldest mini-Neptunes, helium can also condense, forming helium rain or helium oceans at great depth, adding yet another layer of exotic behavior. Finally, some planets display unusual color signatures caused by exotic chemistry. Transmission spectra have revealed strong absorption features from titanium oxide, vanadium oxide, or chromium hydride, molecules that are stable only at very high temperatures. These compounds create sharp, narrow absorption bands, making the atmosphere appear almost black at certain wavelengths, or strangely colored when light passes through the limb. Other planets show evidence of hazes made of sulfur or hydrocarbon particles, scattering blue light more efficiently, giving the planet a pale, almost whitish appearance in some cases. Every one of these extremes, metal clouds, glass rain, lava oceans, sulfur hazes, metallic hydrogen, diamond rain, helium condensation, unusual absorption bands has been detected or strongly inferred through real observations. Transit spectroscopy, direct thermal imaging, phase curve analysis, all confirm these conditions. And every single feature, no matter how strange it first appears, is produced by the exact same physical laws we already understand. Vapor pressure determines when a substance condenses or evaporates. Phase diagrams dictate which high-pressure ices or fluids can form. Radiative transfer governs how energy moves through the atmosphere. Chemistry follows temperature and pressure. Always. Nothing here breaks the rules. The more extreme the world, the clearer it becomes that the underlying physics is simple, consistent, and everywhere the same. All these wildly different surfaces and atmospheres still obey the same basic rules. Rules we are about to see more clearly. Now, let's pause for a moment and gently look back at the worlds we have explored so far. We began with the planets that hug their stars so closely, the hot Jupiters and ultra-short period worlds, where temperatures climb to thousands of degrees, where metals vaporize into clouds, where atmospheres swell outward and then slowly leak away under relentless radiation, where glass rain falls and rock itself turns to vapor, all in a place that never knows night. Then we moved outward to the rogue planets, those solitary wanderers with no star to call home. Drifting through the cold darkness between systems, their surfaces frozen to near absolute zero, yet some still carrying enough internal heat to keep liquid water hidden beneath thick ice, or to maintain a thin atmosphere against the vacuum. Quiet survivors, carried only by the gentle motion they inherited long ago. From there, we traveled to the cold and distant giants, gas giants and ice giants on extremely wide orbits, receiving only the faintest trickle of starlight, their atmospheres chilled to tens of degrees above absolute zero, their seasons stretching across centuries. Diamond rain falling slowly through their deep interiors, thick hydrogen and helium envelopes preserved for billions of years, reflecting almost no light, glowing only with the weak heat leaking from within. Closer in, we encountered the super-Earths and mini-Neptunes, worlds that sit between the rocky planets we know and the gas giants, super-Earths with masses several times our own, perhaps covered in deep global oceans or wrapped in thick atmospheres that create powerful greenhouse effects, their surfaces possibly shaped by slow plate tectonics under stronger gravity. Mini-Neptunes with low densities, thick hydrogen-helium envelopes hiding possible water layers or exotic ices deep below, hazy upper atmospheres that trap heat and allow only faint glimpses of what lies beneath. And finally, we reached the tidally locked worlds in the habitable zone, planets that forever show one face to their star. One hemisphere locked in endless daylight, the other in eternal night, the day side hot, the night side cold. Yet a narrow twilight ring between them where temperatures might allow liquid water, where thick atmospheres work tirelessly to carry heat from the bright side to the dark, creating global circulation patterns that strive to balance their extremes, symmetric, steady, governed by the same winds and energy flows we understand on Earth. These are not imagined places. They are real, detected through careful measurement of starlight, through tiny dips in brightness, through faint wobbles in stellar motion, through infrared glows and transmission spectra. Hot Jupiters with vaporized iron clouds, rogue planets floating in permanent darkness, distant giants with glacial seasons and diamond rain, super-Earths with deep oceans or crushing atmospheres, mini-Neptunes with fluid interiors hidden under hydrogen, tidally locked worlds divided between perpetual day and night, and among them, The strangest atmospheres we have glimpsed: metal hazes, glass rain, sulfur-rich layers, possible lava oceans, deep metallic hydrogen, helium condensation, exotic high-pressure ices, unusual absorption bands that color the light in ways we rarely see. Each one so different, so extreme, so far from the quiet familiarity of our own solar system. Hot worlds that glow in infrared, cold worlds that drift alone, massive worlds with slow centuries-long seasons, dense worlds with possible global seas, low-density worlds with deep gaseous envelopes, locked worlds with a single twilight zone where water might linger. And yet, all of them exist. All of them are stable. All of them have been shaped by processes we can trace and understand. They are not random. They are not exceptions. They are simply different expressions of the same fundamental rules. Looking back at this wide range, at the scorching heat, the frozen isolation, the glacial distances, the deep oceans and thick gases, the sharp division between day and night, at the metal clouds, the glass rain, the lava surfaces, the sulfur hazes, the diamond layers, the helium oceans. It becomes quiet, almost inevitable to wonder. How can such wildly different worlds all exist together? How can one set of simple laws produce scorching gas giants, dark rogue wanderers, frozen distant giants, ocean-covered super-Earths, hydrogen-shrouded mini-Neptunes, tidally locked twilights, metal clouds, glass rain, lava oceans, sulfur atmospheres, diamond rain, helium condensation, and still hold everything in place? The answer lies just ahead. The more we look at the differences, the more clearly we begin to see the single thread that runs through every one of them. There is an order here, quiet, unchanging, and far more profound than the variety itself. Now that we have looked back at the wide variety of worlds we have explored, let us begin to see what ties them all together. We start with the simplest and most fundamental force: gravity. Gravity is the first law at work in every exoplanet we have discussed, and it explains so much of the diversity we see. Even before we consider temperature, chemistry, or atmospheres, consider first the orbits themselves. Every planet we have visited, whether it circles very close to its star, drifts alone in interstellar space, or travels at vast distances, follows a path determined entirely by gravity. For the hot Jupiters and ultra-short period planets, gravity from the host star pulls them into tight, nearly circular orbits very near the star. The closer the orbit, the stronger the gravitational force, the faster the planet must move to remain in balance, completing a full revolution in days or even hours. This same gravitational pull shapes the planet's structure, compressing its interior, increasing pressure with depth, helping to hold thick hydrogen-helium envelopes in place despite the intense heat. Gravity also determines why these close-in worlds are often tidally locked. The star's gravitational gradient across the planet's diameter creates a torque, gradually slowing the rotation until the planet's spin matches its orbital period. One face always toward the star, the other always away. This locking happens over millions or billions of years, a slow, patient process driven purely by gravitational interaction, and once achieved, it remains stable, unless an external force intervenes. Now move outward to the rogue planets. These worlds began in the same way, forming in protoplanetary disks, accreting mass under gravity's pull, just like any other planet. But in some systems, gravitational encounters with other massive bodies, perhaps sibling planets or a passing star, become strong enough to increase the planet's velocity beyond the escape speed of its original star. Once that threshold is crossed, gravity no longer holds it in orbit and the planet is ejected, carrying away only the momentum it had at that moment. After ejection, gravity from the galaxy as a whole, from distant stars, from dark matter, continues to act, gently curving the path over millions of years, but never enough to capture it into a new orbit in most cases. The rogue planet drifts, free, yet still obeying gravity at every step, its trajectory a long, quiet arc through the galaxy. For the cold and distant giants, gravity again sets the scale. At hundreds of astronomical units, the star's gravitational influence is weak, so the orbital velocity is low, and the period becomes extraordinarily long, thousands or tens of thousands of years. Gravity still binds the massive hydrogen-helium envelope to the core, preventing escape, even though the temperature is low and stellar radiation is faint. The same force compresses the deep interior, raising pressure until exotic phases form. Diamond rain in ice giants, metallic hydrogen in gas giants, all because gravity squeezes matter tighter and tighter with depth. Even the capture of moons or rings around these distant worlds, when it happens, is a gravitational process. Temporary satellites or particles settling into stable orbits under the planet's own gravity. Gravity also shapes the formation history of super-Earths and mini-Neptunes. In the protoplanetary disk, gravity causes dust and pebbles to clump, planetesimals to grow, and cores to accrete gas when they reach a critical mass. Super-Earths, forming closer in, accrete rocky material rapidly, but the disk dissipates before runaway gas accretion can occur, so they remain mostly rocky, with only a modest atmosphere held by their own gravity. Mini-Neptunes, forming slightly farther out, reach the critical core mass sooner, capture thick hydrogen-helium envelopes, and retain them because their gravity is strong enough to prevent significant loss, even over billions of years. Gravity determines the balance, how much atmosphere a world can keep, how dense its core becomes, how it responds to migration through the disk. And on tidally locked worlds, gravity creates the very geometry we discussed, the torque that enforces synchronous rotation, the division into permanent day and night, the tidal bulges that drive internal heating if the orbit is slightly eccentric, all rooted in gravitational forces. Across every category, gravity acts as the architect. It sets orbital distances, which control how much stellar energy arrives. It determines whether a planet stays bound to a star or becomes rogue. It compresses interiors, enabling high-pressure chemistry and exotic matter. It holds atmospheres, decides whether they escape or remain. It shapes migration, tidal locking, capture of moons, the entire framework within which temperature, Chemistry and circulation play out, and yet gravity alone does not explain everything. It sets the stage, places each world in its position, gives it mass, holds it together. But temperature extremes require another law to explain them. These temperature differences are governed by energy transfer. Now that we have seen how gravity places each world in its position, sets its orbit, holds its mass together, let us look at the next fundamental law that shapes their conditions: thermodynamics, the physics of heat and energy. Every exoplanet we have visited, from the hottest close-in worlds to the coldest distant ones, has its temperature determined by the same basic principles of energy balance. The first and most important source of energy is stellar radiation. A star emits light and heat across a wide range of wavelengths, and the amount a planet receives depends on three simple factors: the star's luminosity, the planet's distance from the star, and the planet's ability to absorb or reflect that energy. For hot Jupiters and ultra-short period planets, the distance is very small, so the flux of stellar radiation is enormous, often thousands of times greater than what Earth receives from our Sun. This intense incoming energy is absorbed by the atmosphere and the upper layers, heating them to thousands of degrees, driving thermal emission, vaporization of metals, and the swelling of the gas envelope. The planet radiates energy back to space, but because the incoming flux is so high, equilibrium is reached only at very high temperatures, where the outgoing radiation matches the absorbed energy, according to the Stefan Boltzmann law. The balance is precise. The same law that determines Earth's average temperature, simply applied to a much larger incoming energy budget. Now move to the other extreme, the rogue planets and the cold distant giants. Here, stellar radiation is either completely absent in the case of rogues, or reduced to a tiny fraction for wide orbit worlds. With almost no external energy input, these planets cool over time, losing heat through their own thermal radiation. Yet they do not cool indefinitely to absolute zero. During formation, gravitational contraction and accretion released enormous energy, much of which was trapped inside as heat. Radioactive decay of elements in the core and mantle continues to generate energy, slowly but steadily over billions of years. This internal heat flows outward through conduction, convection, and sometimes even small-scale mantle plumes, keeping the deep interior warmer than the surface. The surface radiates this heat to space, but the thick atmospheres or ice layers on some worlds act as insulators, slowing the loss, allowing subsurface oceans or fluid layers to persist. The energy balance here is again exact. Incoming heat from the interior equals outgoing radiation, but with no star involved. Equilibrium settles at very low temperatures, often tens of degrees above absolute zero. Even on tidally locked planets, thermodynamics governs the sharp contrast between hemispheres. The day side receives steady stellar flux, absorbs it, heats up, and radiates strongly. The night side receives none, cools rapidly, and radiates weakly. Without an atmosphere, the temperature difference would be extreme, the day side scorching, the night side near absolute zero. But when an atmosphere is present, Heat is transported from the day side to the night side, through winds, advection, and sometimes latent heat carried by condensing volatiles. The efficiency of this redistribution depends on the atmospheric mass, composition, and wind speeds. But the underlying principle remains the same. Energy must balance. Incoming on one side, outgoing on both, with transport moving the excess from hot to cold. Greenhouse effects amplify this further. On super-Earths or tidally locked worlds with thick atmospheres, molecules such as carbon dioxide, methane, or water vapor absorb outgoing infrared radiation, trapping heat near the surface. This greenhouse warming raises the equilibrium temperature, sometimes by hundreds of degrees, allowing liquid water to exist even when the planet receives relatively little starlight, or on the night side of a locked world. The same greenhouse mechanism that warms Venus to extreme levels, or keeps Earth habitable, operates on these distant worlds, simply scaled by atmospheric thickness and composition. Internal heat also plays a role on many worlds, not just the rogues. On mini-Neptunes, residual formation heat and slow contraction keep the deep interior warm, driving convection that mixes the envelope, transports heat upward, and maintains temperature gradients that shape cloud layers and haze formation. On ice giants, gravitational compression and radioactive decay provide energy, enough to power slow diamond rain or fluid motion in high-pressure water layers. In every case, the temperature, whether thousands of degrees on a hot Jupiter or tens of degrees above absolute zero on a distant giant, is the result of energy in equaling energy out. Stellar radiation provides the input for close-in worlds, internal heat for isolated or distant ones. Greenhouse trapping modifies how that energy is retained. Atmospheric circulation moves it around, and radiation to space removes it. No exceptions, no special rules for distant places. The same four processes: absorption of incoming energy, internal generation, transport, and radiative loss. Explains scorching day sides, frozen night sides, subsurface oceans in darkness, diamond rain in cold interiors, glass rain in heat, lava oceans under relentless flux. All of it. The laws are simple, the same everywhere. The same equations that describe a star's energy output, Earth's climate, or a cup of tea cooling on a table. We see scorching worlds, freezing worlds, locked worlds, rogue worlds, giants, super-Earths, mini-Neptunes, all with temperatures shaped by this quiet balance. The differences arise only from distance, mass, atmosphere, and time. But the principle never changes. These temperature differences are governed by energy transfer. Yet the atmospheres we see are even more varied. Chemistry shapes what we see on the surface, but the variety begins with the molecules themselves. Now that we have seen how gravity positions each world and how thermodynamics sets its temperature, let us look at the next layer: chemistry. The way atoms and molecules combine, react, condense, and form the gases, clouds, hazes, and surfaces we observe. The atmospheres of exoplanets are built from the same basic elements found throughout the universe, mostly hydrogen, helium, carbon, oxygen, nitrogen, and traces of heavier atoms, but the proportions, temperatures, and pressures determine which molecules dominate and how they behave. On many hot Jupiters and ultra-short period planets, the upper atmosphere is rich in hydrogen and helium, the two lightest and most abundant elements. At temperatures of 1,000 to 3,000 degrees Celsius, these simple molecules remain gaseous, but other compounds become stable. Water vapor, if present, dissociates into hydrogen and oxygen, while carbon monoxide often becomes more abundant than methane because high heat favors CO over CH4 in equilibrium chemistry. Titanium oxide and vanadium oxide, stable at these temperatures, can form in the gas phase, then condense into tiny solid particles when carried to slightly cooler regions, creating metal oxide clouds that absorb light strongly, making the planet appear very dark in visible wavelengths. Silicates, compounds of silicon and oxygen, vaporize on the hottest day sides, then condense as droplets or grains, producing silicate clouds or the glass rain we mentioned earlier, all following equilibrium condensation sequences that depend only on temperature and pressure. On cooler worlds, such as some mini-Neptunes or tidally locked planets in the outer habitable zone, lower temperatures allow different molecules to dominate. Methane, CH4, becomes stable, especially when carbon is abundant relative to oxygen, and can form thick haze layers through photochemical reactions triggered by stellar ultraviolet light. These hazes, made of hydrocarbon particles, scatter light, often giving the planet a grey or brownish appearance in transmission spectra. Water vapor, A2O, remains gaseous in the upper atmosphere and can condense into water clouds at certain altitudes, especially on worlds with enough cooling. Carbon dioxide, CO2, appears in atmospheres where oxygen is more abundant and can drive strong greenhouse warming, raising surface temperatures well above what the incoming stellar flux alone would allow. Ammonia, NH3, forms in colder regions, particularly on ice giants or mini-Neptunes with nitrogen-rich compositions, and can condense into ammonia clouds or dissolve into water layers, contributing to the hazy or colored appearance of these envelopes. On some super-Earths with thick atmospheres, high pressure at depth forces molecules into exotic states. Water under thousands of bars becomes supercritical fluid, neither liquid nor gas, flowing like a dense liquid but with gas-like properties, dissolving salts or other compounds in ways that resemble deep Earth oceans, but on a planetary scale. Methane and carbon monoxide, under similar conditions, can dissociate or recombine, forming more complex hydrocarbons or carbon-rich ices. The cloud decks on these worlds, whether water, ammonia, methane, or silicate, form at specific altitudes where the temperature and pressure cross the condensation curve for each species, creating layered structures much like the cloud layers in Jupiter's atmosphere, but scaled to different temperatures and gravities. Photochemistry adds another layer of variety. Stellar ultraviolet light breaks apart molecules in the upper atmosphere, producing free radicals that recombine into heavier species, such as sulfur compounds, hydrocarbons, or metal hydrides. These photochemical products can form hazes that persist for long periods, scattering blue light more than red, sometimes giving the planet a pale or unusual tint when observed during transit. On sulfur-rich worlds, hydrogen sulfide or sulfur dioxide can photolyze, forming elemental sulfur particles which condense into yellow or red hazes, altering the spectrum in distinct ways. All of these processes, molecular equilibrium, condensation, photochemistry, haze formation, are governed by the same chemical kinetics and thermodynamics we study in laboratories on Earth. The temperature sets which molecules are stable. The pressure determines densities and condensation levels. The incoming ultraviolet flux drives dissociation and recombination, and the composition of the original disk, reflected in the planet's overall metallicity, sets the abundance of heavier elements like carbon, oxygen, nitrogen, and sulfur. There is no need for exotic new chemistry, only the familiar reactions, pushed to different temperature, pressure, and radiation regimes. A hot Jupiter with titanium oxide clouds, a mini-Neptune with methane haze, a super-Earth with supercritical water layers, a tidally locked world with water vapor on the day side and ammonia clouds on the night side. All emerge from the same periodic table, the same bond energies, the same phase diagrams. The variety is immense, yet the rules are few, simple and universal. We see metal clouds, glass rain, hydrocarbon hazes, sulfur particles, supercritical fluids, exotic ices, all formed by the quiet work of chemistry under different conditions. Chemistry shapes what we see on the surface. But what keeps these worlds stable over time? All these forces work together under a small set of rules. Rules that never change. We have seen gravity position the worlds. Thermodynamics set their temperatures. Chemistry shape their atmospheres and surfaces. Now let us look at what allows these wildly different planets to remain stable, to endure over billions of years, despite the extremes of heat, cold, pressure, and radiation. The first key is orbital stability, the long-term balance that keeps a planet in its path without spiraling inward, being ejected, or colliding with other bodies. Every orbit we have described, whether a hot Jupiter's 4-hour loop, a rogue planet's straight drift through the galaxy, a distant giant's 10,000-year circle, or a tidally locked world's synchronous rotation, is stable because of gravitational equilibrium. The planet's orbital velocity exactly balances the gravitational pull from the star. Or, in the case of rogues, the lack of a strong central force allows free motion. For planets in multi-planet systems, additional stability comes from orbital resonances. When two planets share a simple ratio of orbital periods, such as 2 orbits to 1 or 3 to 2, their gravitational tugs reinforce each other at regular intervals, but in a way that keeps the orbits locked and prevents chaotic scattering. These resonances are common, especially in tightly packed systems, and they can last for the lifetime of the star, quietly maintaining order among otherwise close neighbors. Tidal forces also play a role in long-term stability. On close-in worlds, strong tidal interaction with the star circularizes the orbit over time, damping any initial eccentricity, so the planet settles into a nearly perfect circle reducing the chance of dramatic heating variations or collisions. The same tidal forces that cause locking also dissipate orbital energy as heat. But once locking is achieved, the energy dissipation slows and the orbit becomes even more stable. For planets farther out, weaker tides mean less orbital evolution. So wide orbits remain nearly unchanged for billions of years, preserving the cold conditions we see on distant giants. Now consider radiation balance, the long-term protection against the constant stream of stellar particles and high-energy photons. Every star emits not only light, but also a wind of charged particles, protons, electrons, and heavier ions, traveling at hundreds of kilometers per second. On planets close to their stars, this stellar wind is intense, and without protection, it can strip atmospheres over time, especially light hydrogen and helium. Yet many hot Jupiters and ultra-short period worlds retain substantial envelopes because their own gravity is strong enough to hold the gas against the wind, or because a magnetic field generated by internal convection in metallic hydrogen layers deflects much of the charged particle flux. The interaction creates a bow shock ahead of the planet, much like Earth's magnetosphere, but shaped by the planet's gravity and magnetic strength, carving out a protected region where the atmosphere can persist. On tidally locked worlds in the habitable zone, especially around red dwarfs, stellar wind and flares are a greater concern, because the close orbit brings the planet deeper into the star's particle outflow. But here too, a global magnetic field can provide shielding, deflecting charged particles away from the atmosphere, preventing gradual erosion. Even without a strong field, a thick atmosphere itself acts as a buffer, absorbing and scattering incoming radiation, creating a gradual pressure gradient that slows escape. For super-Earths and mini-Neptunes, higher gravity and denser envelopes make atmospheric retention easier, so they can hold hydrogen-helium layers or water-rich atmospheres against stellar wind for billions of years. Rogue planets, far from any star, face cosmic rays instead of stellar wind, high-energy particles from supernovae and active galactic nuclei. But their thick atmospheres or icy shells provide natural protection, slowing the erosion of any subsurface volatiles. The habitable zone itself, the range of distances where stellar radiation allows liquid water on the surface, is another expression of radiation balance. Closer to the star, the flux is too high, leading to runaway greenhouse effects like Venus or complete atmospheric loss. Farther out, the flux is too low, freezing surface water, as on Mars. But in the right narrow band, incoming energy balances outgoing radiation, allowing stable surface temperatures near the freezing and boiling points of water, especially when an atmosphere adds greenhouse warming. This zone shifts outward for larger, hotter stars, inward for smaller, cooler ones. Yet the principle remains identical. Energy in equals energy out, modulated by distance and atmospheric properties. All of these mechanisms, orbital resonances that lock paths, tidal damping that circularizes orbits, magnetic deflection of stellar wind, atmospheric buffering, gravitational retention of envelopes, habitable zone placement, work together to ensure long-term stability. A hot Jupiter keeps its swollen atmosphere despite intense radiation. A rogue planet preserves subsurface heat and ice despite cosmic rays. A distant giant maintains its thick envelope despite weak stellar input. A tidally locked world sustains a twilight zone despite extreme hemispheric contrast. A super-Earth or mini-Neptune retains its composition despite close orbits or flares. None of these outcomes require new physics, only the consistent application of gravity. Orbital mechanics, magnetic interactions, and radiative equilibrium. The extremes do not destabilize the worlds, they reveal how robust the balance truly is. These planets endure, not by accident, but because the forces that shape them are steady, predictable, and universal. All these forces work together under a small set of rules. Rules that never change. Now, we arrive at the quiet heart of everything we have explored. Let us rest here for a moment and simply look at what has unfolded. We have traveled from worlds scorched by relentless starlight, where metals rise as vapor and glass falls as rain, to worlds lost in eternal darkness, drifting alone with hidden oceans beneath their ice, to distant giants wrapped in glacial seasons and diamond rain, to super-Earths carrying deep global seas or thick crushing atmospheres, to mini-Neptunes shrouded in hydrogen with fluid layers far below, to tidally locked planets divided perfectly between endless day and endless night, and finally to the strangest atmospheres of all: metal clouds, sulfur hazes, silicate rain, lava oceans, metallic hydrogen, helium condensation, exotic ices, unusual colors painted by molecules we can name and measure. So many extremes, so much apparent strangeness, so many conditions that seem to belong to entirely different universes. Yet, as we hold all these worlds in our mind at once, something gentle begins to emerge. The more different the worlds appear, the more clearly we see that the same few unchanging laws govern everything. Gravity that places them in their orbits, that compresses their interiors, that holds their atmospheres or sets them free as rogues. Thermodynamics that balances incoming energy with outgoing radiation, that sets scorching daysides and frozen nightsides, that allows internal heat to preserve oceans in darkness, or drives winds to carry warmth across hemispheres. Chemistry that arranges atoms into water vapor, methane, carbon dioxide, titanium oxide, sulfur compounds, silicates, hydrocarbons, all following the same bond strengths, the same phase boundaries, the same reaction pathways, only expressed under different temperatures and pressures. Orbital mechanics that lock resonances, damp eccentricities, preserve paths across billions of years, radiation balance that shields with magnetic fields, buffers with thick air, defines habitable zones, protects subsurface layers from cosmic rays. Every feature we have seen, every metal cloud, every glass rain, every diamond sinking slowly, every twilight ring where water might linger, every haze scattering light, every lava sea glowing in infrared, arises from these same simple rules. The universe is not chaotic. It is profoundly, peacefully lawful. The same laws that create these extreme worlds are the same laws that quietly hold our own planet together right now. The gravity that keeps the moon circling Earth is the gravity that flings a rogue planet into the void or binds a hot Jupiter in its tight embrace. The thermodynamics that warms our atmosphere just enough for liquid oceans is the thermodynamics that scorches a day side to thousands of degrees or preserves heat beneath kilometers of ice on a starless world. The chemistry that forms rain clouds here is the chemistry that builds silicate clouds there or methane hazes on distant worlds. The orbital stability that has kept Earth circling the Sun for 4.5 billion years is the same stability that keeps a tidally locked planet showing one face forever, or allows resonances to organize entire systems. Nothing is separate, nothing is random. The laws are few, they are constant, they are everywhere. The more wildly the worlds differ, the more reassuring this becomes. A scorching gas giant, a frozen rogue, a twilight world with possible seas, our own blue-green home, all rest on exactly the same foundation. We belong to that same order. Our planet, our atmosphere, our oceans, our slow-turning days are not exceptions. They are simply one more expression of the same quiet rules that stretch across the galaxy. This is not a cold realization. It is a warm one, a gentle one. The universe is lawful, deeply, peacefully lawful. And we are already inside that lawfulness. Right now, as we breathe, as we rest, the same unchanging forces continue. Gravity holds us gently to the ground. Thermodynamics keeps our world at a temperature where water flows. Chemistry builds the air we draw in. Orbital balance keeps our path steady. Everything remains steady. The same laws continue. The quiet order holds. Everything remains steady. You are already inside this order. The same laws continue. The quiet order holds. Everything remains steady. Now let us rest here, very gently, and allow everything we have seen to settle quietly. We have traveled so far together, from scorching worlds where metals rise as vapor and glass falls as rain, to solitary rogues drifting in permanent darkness, to distant giants wrapped in centuries-long seasons, to super-Earths carrying deep oceans beneath thick air, to mini-Neptunes hiding fluid layers under hydrogen, to tidally locked planets divided between endless day and endless night, and to atmospheres filled with metal clouds, sulfur hazes, silicate rain, lava seas, diamond rain, helium condensation, exotic ices, unusual colors, all of it real, all of it measured, all of it explained. And through every step, the same quiet truth has become clearer. The more different the worlds appear, the more clearly we see that the same few unchanging laws govern everything. Gravity that places them, holds them, shapes them. Thermodynamics that balances their heat, warms their day sides, cools their night sides, preserves hidden oceans in darkness. Chemistry that builds their molecules, their clouds, their rains, their hazes, their surfaces. Orbital mechanics that keeps their paths steady, their resonances locked, their orbits enduring. Radiation balance that protects, shields, defines the narrow bands where water can linger. The universe is not chaotic, it is profoundly, peacefully lawful. The same laws that create these extreme worlds are the same laws that quietly hold our own planet together right now. The gravity that keeps our moon circling is the gravity that binds a hot Jupiter or lets a rogue drift free. The energy balance that warms our oceans is the energy balance that scorches a dayside or keeps heat beneath ice on a starless world. The chemistry that forms rain clouds here is the chemistry that forms metal clouds there, or methane hazes far away. The orbital stability that has carried Earth safely for billions of years is the same stability that keeps a tidally locked world showing one face forever, or allows resonances to organize entire systems. There is no separation. We are not outside this order, we are inside it. The calm, lawful universe that allows such astonishing variety is the same universe quietly surrounding us right now. Right now, as you rest, as your breath moves gently, the same unchanging forces continue. Gravity holds you softly to the ground. Thermodynamics keeps the air at a temperature where you can breathe comfortably. Chemistry builds the molecules in every breath you take. Orbital balance keeps our world turning steadily. Day following night, season following season. Everything remains steady. The same laws continue. The quiet order holds. Everything remains steady. You are already inside this order. The same laws continue. The quiet order holds. Everything remains steady. The gravity that shaped distant worlds still holds the moon in its gentle arc around us. The energy balance that allows extreme temperatures elsewhere still keeps our planet mild enough for life. The chemistry that creates metal clouds and glass rain far away still forms the water in our rivers, the air we share. The orbital paths that endure for billions of years still carry us safely through space. There is no place outside this lawfulness. There is only this quiet, consistent, peaceful order, and we are part of it. Right now, in this moment, the same rules that govern a rogue planet drifting alone govern the turning of our own world. The same rules that balance a scorching dayside balance the warmth on your skin. The same rules that form diamond rain in a distant giant form the simple chemistry of every cell in your body. Everything remains connected. Everything remains steady. The same laws continue. The quiet order holds. You are already inside this order. Let your breath slow. Let your thoughts soften. Let the gentle rhythm of these words carry you. The same laws continue. The quiet order holds. Everything remains steady. You are safe, held, part of this vast, lawful, peaceful whole. The same laws continue. The quiet order holds. Everything remains steady.